adjoint formulation that constitutes the core of the methodology called 4D-WAR. It goes by different names: variational methods, first order adjoint method, 4D-WAR. They all are different names for the same object. The object is to be able to develop an algorithm. To be able to get to the so-called first order adjoint algorithm or the method, I would like to start by quickly reviewing some of the mathematical fundamental tools we need to be able to build that algorithm. So I'm going to start by defining what is the first variation, what is the second variation, how do we quantify the first variations, and that's the first fundamental idea. The second fundamental idea is what is adjoint and what are the properties thereof. Once we know these two mathematical tools, we should be ready to be able to develop the tools. There are two ways of doing it. In our book, we first do for the linear dynamics, and then we do for the nonlinear dynamics. I'm going to straight away do for the nonlinear dynamics, and then specialize to linear cases when things are appropriate. So that way we can kill two birds in one stone. Are you with me? Okay. So I'm going to be starting with the definition of variation. So let f of x be a function of x. I'm going to perturb the point x plus, let us say, delta x. If I perturb, the value changes. We generally denote the change in value of f as del f, which is x plus delta x minus f of x. When you do Taylor series expansion, sometimes we'll assume let x plus h be a point in a closed neighborhood of x. So this vector h is a perturbation. Instead of using h, which we have done so far, I'm simply changing the notation as delta x. So delta x is a small increment. So here again comes the notation. In basic calculus, we will say let delta x be an increment. So I am now using delta x is equal to delta x. Are you with me? Let delta x be an increment. So how do we say in differential calculus? Y is equal to f of x. Let delta x be the change in x. Let y plus delta y be the change in that. Then you define the differential coefficient and so on. So in the conventional calculus, we use this symbolism. Now I am using this symbolism. In a way, you can think of this, there are all changes in x, perturbations in x. Sometimes we use this letter, so they all mean the similar things. It is simply the notation changes from time to time by convention. So I don't think you should be overly perturbed by that. Now I'm going to be able to express this in the form of a Taylor series. The first term will be f of x. So that will cancel with this. So what will be the first term in here? Now let me assume my f is a function from Rn to R. So the first term will be inner product of del f del x, which sometimes we write this as del f transpose d of x. Right? That's the first term. The second one is 1/2 of del x del square f del x in the quadratic form plus 1 and so forth. So I'm going to keep this inner product notation. Again, this inner product notation we should all be familiar with. A bracket b is equal to A transpose b, which is equal to B transpose A, which is equal to BA. Inner product is symmetric. It can be thought of as a bilinear form. So that's the same notation I'm using. So this term, okay, now, so if I perturb x, Taylor series tells you that this perturbation in x induces a sequence of perturbation that can be quantified using the first derivative, second derivative, third derivative, and so on. at sometimes, for a computational perspective, I'm going to chop that expansion to get a finite representation so that I can easily do arithmetic numerical work. So this term is generally denoted by del f. This is called the first variation. This is called the second variation. So if I'm doing a first order approximation, the actual change in f resulting from the change in delta x is going to be approximated by the first variation. That's an approximation. The actual change in f being approximated by first variation plus del square f second variation. That will be a second order method. You can even put 1/2 in here. Second variation. So in first order adjoint method, we are going to be capturing only that part of the actual change induced by the first variation. In the second order method, we will capture the sum of the first and second variation. First variation is related to the first derivative, second variation is related to second derivative, and so on. So in variational methods, the order of the variation is important. First order method, second order method. So given a function, now I need to be able to have good facility with computing the first variations, and that's what I'm going to do next. But before we go further, I would like to be able to get the formula. The first variation in f is given by the inner product of the gradient of f with the perturbation in x. This is also in multivariate calculus known as the directional derivative. This is also called directional derivative. This is the inner product of the gradient in the direction delta x. Right? Delta x is the unit vector. It is simply a projection of the gradient in the direction delta x. So this is directional derivative.
Diagnostic. Now detailed causalistic.
Directional derivative. First variation, and so on. In today's talk, I'm going to confine myself only to first order method, first variation.
So 99, so we are receiving more, transmitting less. Yes, right, yes. At some
time this, we can come back and do the arithmetic of the derivation of the adjoint method rather easily. So let's get going. Suppose I have a function phi of x is equal to ax. The first variation phi is equal to a times the directional derivative. In order to compute the directional derivative, you need to have the gradient and then fix the direction. So if this is the gradient, is the direction I want to compute the directional derivative, you simply take the net product. That's the idea here. That's the idea here. So let's quickly tabulate some of the functional forms of some of the things I need for our discourse. So this is the first one. The second one, if phi of x is equal to 1/2 of x ax, then the first variation of this is equal to ax delta x. Verification of each of these things are homework. It is absolutely essential that we have a good facility with computing these fundamental quantities. Once you succeed in doing this, adjoint method is a child's play. Out with me? That's right. So what is the next one? The next one is, let phi of x is equal to 1/2 of z minus h of x, comma, or inverse z minus h of x. You remember that? The terms of this kind keeps coming again and again and again. So the del in this case is equal to h transpose or inverse hx minus z times delta x. So what do you need to do? You need to compute the gradient, which we have already seen. You need to compute the gradient, which we have already seen. So I'm not going to repeat that. That's why I'm trying to quote these formulas. Verification of this is an easy exercise, and you must do that. The fourth one is phi of x is equal to h of x. Look at this now. Here is simply a linear function. This could be a nonlinear function. Inner product of A with a nonlinear function. In this particular case, del phi is equal to the Jacobian of h of x. Jacobian of now the fifth formula is that, let me change my color. The fifth formula we need is if phi of x is equal to 1/2 of h of x, A of h of x. Okay, here I'm assuming tacitly things. A is a vector. H of x is a vector valued function of a vector. And these two are vectors that are compatible in size. This is the net product of a scalar with the vector valued function of a vector. We are talking about the first variation of that. So the first variation of that product is the transpose of the Jacobian of h times h of x. Okay, now for this, the first variation is dh transpose x A h of x. One more, your phi of x is equal to 1/2 of z minus h of x, h of x, comma, or inverse z minus h of x. That then del phi is equal to dh transpose or inverse h of x minus z, comma, delta x. These formulas are your best friend when you do this, and I want you to remember all these formulas are tabulated in Appendix C, of which you have a copy already. It is in page 721, Appendix C, Taylor series expansion and first variation. So all these things are tabulated. All of it? Good. The second set of, I'm going to keep this for a moment. The second set of concepts we need is the notion of adjoint. The notion of adjoint can be as complex as you want it to be. I'm going to make it very specific and simple. I'm going to discuss the notion of an adjoint operator in the context of a finite dimensional vector space. In a finite dimensional vector space, linear operators are represented by matrices. So I will use the term operator and matrices interchangeably. So within this context of finite dimensional vector space where linear operators take the form of matrices, I'm going to define adjoint. But yes? What's that? Let me check. One second. I hope I didn't. Oh, the fourth model should be A. That's right. Thank you, sir. Thank you. That's correct. That's A. Okay, so consider a matrix A in my consider the bilinear form x, y. We all know that this is equal to Ax transpose y, that is equal to x transpose ay, and that can be written as x transpose y, All of it, me? Hey, that's the comes from here. So in general, how do you define a joint? If Ax is equal to y, there exists an operator A star such that x A star y. So given A, there exists an operator A star. There are appropriate domains, codomains have to be defined. I'm not going to go much into the details, but I would like to look at it all from the finite dimensional perspective. If given A, two vectors in a vector space, A is operator in the vector space, that exists, given A, there is an associated operator A star that makes this equality. Such an operator is called the joint of A. From here, in the finite distributed vectors case, a joint is essentially given by the transpose. Transpose is that joint. You can talk about the joint of a differential operator, a joint of an integral operator, a joint of any meaningful operator, linear operators, but I'm not going to go there. If A is equal to A transpose, then A is called self-adjoint. Self-adjoint. So in here, I'm assuming A is a general case, and here is A is symmetric. Okay. There's one more little property we would need. That's as follows. A x1 plus x2 is equal to 8 times x1 plus 8 times x2. This is the essential linearity property of the inner product. So this is property 2, this is property 3, all these are property 1, variation, adjoint, and the property of the inner product. Once we have all these three, we're ready to, these are, to me, to use the cooking analogy, these are the ingredients. Now I'm going to cook the food. What is the ultimate food that I'm going to cook? The algorithm for first order adjoint method. Good. All of you? Good. So 4D var is another name for this. So what is that I'm assuming? I'm given a dynamic model. The dynamic model I'm going to straight away deal with the nonlinear model. So let xk plus 1 be the state of a system which is given by xk. I can throw in a parameter alpha if you like. So what is xk? Xk is the state of a system that sits in an n-dimensional space. M is called the one-step transition matrix. One-step transition matrix. One-step transition function or a one-step transition map. In the case of nonlinear system is a map. The M maps Rn. So this is Rn. What is alpha? Alpha is a parameter. The parameter alpha could in general sit in a p-dimensional space. So M is a map from R to Rn. So it takes the current state and the values of the parameter, it spits out a vector that is going to be a future state. So the system evolves in time, in discrete time. K plus 1. And so given xk alpha, this is going to be defined xk plus 1. This map is given by M. That's called the one-step transition matrix. And how do we get this? Suppose we are given a primitive equation. You embed a grid. You discretize that grid. You discretize the differential equation on that grid. You have a finite difference representation. So you convert a nonlinear partial differential equation into a nonlinear difference equation. This is the difference equation. Or you have just like what David was talking about yesterday, you have a nonlinear coupled system of equation that describe the climatology, and then you convert this into a system of ODE by doing a spectral methodology. You project the infinite dimensional representation into a finite dimensional subspace of M modes. He said M is the order of 300. You remember that? That's right. Then you discretize that differential equation ODE. Ultimately, you have to, whatever you start from, ultimately you have to convert everything into a discrete form. So almost all the model codes that they implement the big models are essentially captured by this basic fundamental relation, one step. This one step could be a few minutes, few days. All of it there? Good. So I'm not going to go into how to get this, but this is the starting point for us. Could I have derived the 4D var derivation of 4D var methodology within the continuous framework? Yes, we could. But then that's mathematically beautiful and pleasing. But ultimately, you have to come down. So what is the idea here? Continuous model, continuous adjoint, discrete model, discrete form of adjoint. You do this, you do this, you do this. Sometimes the whole question is this. If you discretize the model and do a discrete adjoint, your continuous model, continuous adjoint, and then discretize this, do they commute? All of me? That's a question that one has to always wonder, and sometimes there may be difficulties in numerically trying to derive from the continuous adjoint. So in most of the models, this is the path that is preferred. Continuous state model, discretize it. After this, once you discretize it, you get this. From here it goes to that. Are you with me? And then I have zk is equal to h of xk plus vk. So this is the model. This is the observations. My zk, so let me talk about all the animals in here. And m is a function from Rn cross Rp to Rn. H is a function from Rn to Rm. Vk is normal Rk. So I'm assuming my model is deterministic. Does it have model error? I don't know. I have incorporated all the knowledge I have. This question has come up again and again. Are you with me, please? That's right. This model tells or represents the present state of my understanding of the physical processes in question. This is the best model I can find on the face of the earth. Will this model have, just because it's the best model I know, is it a good model? No, this is the only thing I have. I don't have any alternative. Does it have error? You betcha. I'm not going to model the errors. So if I put in here a term, a stochastic term, this becomes a stochastic dynamics. That's what we will start with when we do Kalman filtering, the lecture on Tuesday. But today I'm going to start with a deterministic model. Observations are noisy. I know the observation noise properties. X0 is the initial condition. I'm assuming my model solution. So if I have a model solution xk is a function of x0, alpha, and k. Well, I don't have to put a k here. That's a k here. So the model solution depends on the initial condition, depends on the parameter. I'm assuming that the model is such that the conditions and the model solution depends on the initial condition parameters smoothly. All good things in life. All good things in life. So given this, what's the plan or what's the problem? I'm going to have observations of the system. Let us say Z1. This is time 0. Z1, Z2, Z3, Zn. Let us just for the fun of it pretend that I have observations at every instant in time. Right from time 1, the system starts with x0. X1, X2, X3, Zk, Xk, Xn. So what's the idea here? I am starting the model with an initial condition x0. I am splitting the solution. I'm trying to predict the observations. This is the model predicted observation, Zk model, h of xk. This is the actual observation. If my model predicted observation, the actual observations are close to each other in some sense, my initial condition is a pretty good condition. So what is the assumption I'm going to make? Let us assume that I know alpha perfectly. So the only way the model solution can depart from the observed value is because my initial condition was screwed up. Okay, could there be a problem in alpha too? Yeah, I could have screwed up my parameters too. So in principle, there could be errors in the values of the parameters and the initial condition, based on which if I start making the forecast, and predict what the observations ought to be using the function h, I'm going to get a model counterpart of the observation, or of the actual observation. If they two differ by too much, my initial condition is not right. So what is the problem? Give her a bunch of observations, find an initial condition such that the model trajectory is close, the model predicted observation, which depends on the model trajectory, are close to the observations in some meaningful norm. This problem is called smoothing. What is the difference between smoothing, filtering, prediction? I plan to define it formally when I do the Kalman filter. So let's take for granted this is called a smoothing problem, and this is not the first time you are hearing this. You heard this Monday morning, bright and early, first lecture, Chris talked about smoothing problem. All of with me? Okay. Is the statement of the problem clear enough? So I could state the problem, find, so how am I going to do that? I have to concoct a criterion function. And how am I going to do that? Z minus h of x, or inverse z minus h of x, summation k is, okay, xk, zk, zk, xk, k is equal to 1 to n, 1/2 of that. Because I'm assuming alpha is known, zk is known, h is known, it's purely a function of x. I'm sorry, this is a purely a function of x naught. Sorry, it's purely a function of x naught. This is, so what is the idea here? Find an x naught that minimizes jx naught. If alpha is not known, I could think of this as a function of j of x naught and alpha. Then I would say find x naught alpha that minimizes j x naught alpha. So there are two versions thereof. Or if you know initial condition, then you can say, I know the initial condition, I believe I have screwed up my parameter, you can represent this as a parameter estimation problem. So this is the initial condition estimation problem, initial condition and parameter estimation problem, or it could be a pure parameter estimation problem. All of it? Set of the problem is clear. So I have all the tools. We are ready to go. So what is it I want? I want to be able to compute. Minimum, I'm working within a continuous state. A continuous space framework where I'm assuming all things are nice and dandy. I can compute the first derivative, second derivative. I'm going to fall back on the classical necessary sufficient condition for minimum. I'm going to have to compute gradient. I need to be able to compute the gradient of this function. This is where the link between variation. So what does this tell you? If you know the gradient, I can compute the first variation. If you know the first variation and the perturbation delta x, I can extract the gradient out of it. So I could compute the gradient either explicitly or using the notions of first variation. All of it? Yeah, I'm now transitioning. I described the problem. Now I have started talking about the methodology for solving problem. Are there any questions on the framework, on the statement of the problem itself? Yeah, go ahead. If I'm assuming, I would like to be able to talk about the methodology for determining the initial condition first. And that's an easy part of the problem. Using 40-watt to be able to estimate the parameter, the mechanics is slightly different, slightly more complex. I just want to walk before I run. We do it in the book. I'm going to do this, the initial conditions in the class. Any other questions, please? Okay. Good. That's a good question. Let's do that now. That question also have come up in many of the discussions we all have had during coffee time or dinner time or breakfast time. That's correct. That's a good point. So what is the idea here? Let us assume I have found an optimal initial condition. So what does it mean? The optimal initial condition trajectory is going to be a better fit for the observation during what is called the assimilation window. So what is the definition of an assimilation window? It is a time period over which you have been given observation. That's the assimilation window. That could be 24 hours, 6 hours, 12 hours, whatever that is. So the idea here is that by my mechanics, the x0 star I found will give a trajectory that best matches the observation in here. So if I started extrapolating my solution beyond that, what is the basic idea in science? The future should resemble the past. The unknown must be similar to the known. And that's what guides us in science, right? The future must be similar to the past. The unknown is similar to the known. So if it did well so far, and if I extrapolate it beyond that time, so long as this forecast horizon is not too large, I can probably put some money on this forecast. That's how the forecast comes in. This is different from the way in which we will forecast in Kalman filtering, where we are going to be doing a sequential or online technique. So this is an offline technique. Why this is an offline technique? You go and measure n observations, bring a sack of observation in a bucket, come to your office, you compute all these things, and then go back, set it up, run the model. Are you with me? So this is an offline technique, it's a smoothing technique, and predictions are made by extrapolating the solution beyond the assimilation horizon. That's right. So how long the assimilation window is depends on how you collect observations, what kind of computational demands your algorithm has, and so on. Yeah. I want to make sure I have answered all his questions before I jump. Are you with me? You have any further follow-up? Good. Okay, go ahead.
In this case, don't we have an influence of past observation on the
Here, this state is a function of all the observations in the future. That's the smoothing part of it.
Won't we have any influence of the past?
Would you have any
influence from the past observations?
which observation?
Suppose you are looking.
I'm starting the assimilation in here. Okay, go ahead. 1 second. Let me.
Can I add?
Please.
If you add the background term.
Yeah, that's right. Oh, yeah, okay. I'm assuming no background term in here, but I don't know. Is that what you want?
Background term will have it.
That's right. Okay. So what is the background term in here? 1/2 of x0 background transpose background initial kind of the background at time 0. x0 minus x0b. That's the background term. Okay. So that could be, that's right, good, thank you. That could be the information that you are carrying from the past. That could be a background. Sure. For simplicity, I'm not including this. Why? This is a simple quadratic term. In the gradient, there's going to be adding another nuisance term, if you like. Once you know it, I don't want to keep repeating it. That's why I didn't choose to put it in. Thank you. Yes, we could have done it to simplify the algebra. I'm not going to. Good, thanks. Any other question, please? Okay. So I want you to remember that this is an offline technique. Okay. So, what is it we want? Now let's look at this now. So this is my x0. Let's assume x0 is the initial condition I start with. From here I get x1 bar. Here x2 bar. I'm changing the notation slightly. That should not bother anybody. So let this be what's called the base trajectory. What is the base trajectory? I'm starting with an initial condition. How do I pick my initial condition? Meteorologists are very clever people. They don't pull things out of the blue sky. They have a pretty good feel, so they think, in the absence of any other information, this would be the best possible guess for the initial state. Let us call that as x0 bar. The solution of the system arising out of this is the barred quantities. Using these barred quantities, if I have zkm is equal to h of xk bar, this is the model predicted observation. The actual observation is zk. If these two differ, then I know the difference is largely due to xk bar. I'm sorry, s0 bar. All of you with me? Come on, guys. Everybody? So what do? I need to change this. If I want to change this means what? I need to perturb this. So I'm going to do a delta x now. Yeah.
So in practice, x naught bar will be the x background.
Exactly. That's right. X naught bar will be the background. So that's a prior, X naught bar includes all the prior information you have, the best guess you have in the absence of any other new information. Okay. So the best guess I started, but I found out by running a model, the best guess is after all not that best. There is a difference between the model predicted observation and the actual observation. The only way, so what does this mean? I need to be able to force the model trajectory such that the model predicted observation will move close to the actual observation. And that I need to do not only here, but at every point in time. So the idea is to be able to force the trajectory. Okay, there are only two ways of changing the solution of the differential equation. One, add a forcing function, or change the initial condition. Are you with me? In the case of in engineering systems, we can force, engineering systems always have a forcing. I have talked with several of you. But in natural system, you simply have to look at Mother Nature, her dance, and look at it with awe. We can't control nature. So there is no control. The only way to be, in other words, there is no external control input I can put in, like controlling an automobile, controlling an aircraft, controlling a chemical plant. These are man-made engineering systems I can control. So in this case, the only way to control the trajectory is to change the initial condition. So in meteorology literature, if you look at this, the initial condition is called a control variable. I'm going to perturb the control variable by delta x naught. So delta x naught is a change in the initial condition. I'm going to get a new initial condition x naught. So this is equal to x naught bar plus delta x naught. From here, I can compute x1, I can compute x2, I can compute xk, I can compute xm, xn. So, are you with me? How many are with me now? Yes. Because I have gotten rid of all the other possibilities. I know alpha, I know m, I know I have chosen the best model money can buy. So, go ahead.
We are assuming that model physics is
We are not assuming. I have TIFR folks, meteorology folks, they have all the money, they are available. So they can have the best minds. They can put the best people to work. They got the best model on the face of the earth. Something goes wrong in the model, I will change the model. I'm not going to be waiting to know my model is good. If my model is good, I will crap everything and then start all over again. Are you with me? This discussion we have had several times. You remember the talk that David had? He had a system of equations in here. They have put tons of money, years of experience, thousands of hours of work. With me? Why? They believe that model, the scientific community decided that model until something new is known is probably the best way to start. With me? Are we good to go? Good. So, I have eliminated all other possibilities. The only way I can change the trajectory is by changing the initial condition. So we call this control. This is the change in the control. I get this, I get this. Now what do I want? I would like to be able to get a new prediction from here. Now these two are different. Are you with me? I'm sorry. H of xk. This is h of xk bar, this is h of xk. What I would like to have? I would like this to be close to zk. And this I would like to be close to zk for all k 1 less than n. In other words, the problem reduces to the following. Find the perturbation of the initial condition delta x naught such that the model solution computed from x naught is equal to x bar naught plus delta x naught, the new initial condition, it evolves to a state such that the model predicted or model counterpart of observations match the observation modulo the noise. Hey, that's what this one is. Everybody with this? Hey, that's where the least mean square criterion comes in. Now what is this? If this is the perturbation in here, this is the perturbation delta x1, this is the perturbation delta x2, this is the perturbation delta xk, this is the perturbation delta xn. How many follow me? Come on guys. If I perturb this, the perturbation changes. So what are the two things I need to compute? I need to be able to compute the first variation of j. First variation of j will, if I look at this now, if I look at this formula is exactly the same as this formula. Everybody, that's why I kept it here. What is the first variation of the one term? Delta x. So if I apply this to the kth term, delta xk. How many of you are with me? So let's write that down. Delta j x naught is equal to summation, I'm simply going to copy that, dh transpose rk inverse h of xk minus zk k is equal to 1pm. Please remember, I want to be able to minimize this. To be able to minimize this, I need to compute the gradient. I can either explicitly compute the gradient, or I can compute equivalently the first variation, because first variation is the directional derivative that contains the information about the gradient as a part of it. So I computed the first variation of this because I know from basic theory that this contains information about the gradient. That's what I'm seeking. I don't have it now, but I will get it because it is hidden here by virtue of the definition of the first variation. Now let's look at this now. dh, given h, I can compute that. rk I know, h I know, zk I know. So every quantity is known. Do I know delta xk? I don't. I only know delta x naught. Are you with me? So what's the next step? The next step is to stop this progression here and count and think about how do we compute or how do we characterize this. So what is this? If I change the initial condition here, how is it reflected in here? How is it reflected in here? How is it reflected in here? And I'm going to be able to compute a first order approximation to delta x1, delta x2, delta xk. Such a computation is called tangent linear approximation. Tangent linear approximation is the terminology used in meteorological circle, but in mathematics it has been known as long as mathematics has been around. It's called variational equation. It's called variation. So what is variational equation? So if you look into books on mathematics, they will call it variational equation. If you talk about the meteorological literature, they will call it tangent linear system. And that's what I'm going to talk about now. So let me still keep this in here. Yes? Where is coming from? Okay.
These are the model forecast at various times.
The solution of the model is called a forecast. The forecast is a solution.
Various times. These are at various times.
Yes. This is a model solution to forecast.
Now when this assimilation is being taking place, suppose 41, so for the solution at x1, won't it have any influence on x2?
That is answered here, sir. They depend. This is called in the stochastic format called Markov models. What is determinism? The underlying principle of Newtonian mechanics is the notion of determinism. What is the fundamental idea of determinism? If I have the information about the present state to know the future, I don't have to know the past. The present summarizes the entire past. So if I know xk, I don't have to know how I got here to look at xk plus 1. That is the embodiment of determinism as captured in this deterministic one-step state transition map. Yeah. Am I, from the face I look at it, I'm not, you and I are not on the same page.
Actually, I was thinking, suppose...
I'm glad he was thinking, right? That's good one. Go ahead.
With x naught known.
X naught is known. So from X naught you compute X1 using this map.
Then again with x1 as an
For X1 you can do that. That's right. So this is the present future, present future, present future. That's right, that's right. That's the embodiment of the principle that underlie the concept of determinism. If I know where the Earth today is with respect to the sun, and the moon with respect to Earth at this time, I can predict the positions of Earth and its moon for all future time using a standard second order differential equation that describes the motion of planets. That's one of the earliest way to describe the fundamental principle of determinism. So our model is deterministic. Good, good. With me now? Good to go? Yeah. Any other question? Okay. So how are we going to do that? So let's do a simple thing now. I had x1 bar is equal to m of x naught bar. Now I'm not going to keep putting alpha. Why? I know alpha. So if I know alpha, I don't have to keep worrying about them. I don't have to carry them. Everybody? I want to simplify. I don't want to write too many things. You get lazy because it's known, it's there, it's a part of m. I don't want to keep reminding myself there is a parameter. So what do I do now? M of x naught bar plus delta x naught. This is called x1. Look at this now. X naught is equal to x naught bar plus delta x naught. I am going to get x1 from here, so that's the thing that comes in here. Everybody? Good. So I'm assuming m is smooth, so I can apply Taylor series. I'm going to be content with applying a first order Taylor series. That essentially tells you m of x naught bar plus dm at x naught bar times delta x naught. This is the Jacobian of the model map. This is a n by n matrix, n by 1 vector. This is a n vector, that's a n vector. But what is this? mx naught from here is x1 bar plus d m x naught delta x naught. So if I kick this to the side, x1 minus x1 bar is equal to, I should not say, I should say approximate equal to, but you know what I'm doing, so I'm going to be a little bit sloppy. I'm going to call it equal. If you know you are abusing notation, you can continue to abuse, right? Because you know you have started abusing it. So this is, but what is this? That's delta x1. So the change in the state at time 1 resulting from the change in the state at time 0 as seen to the model is given approximately by this equation, delta x1 is equal to dm x bar naught delta x naught. Because I know it is x bar naught, to simplify further notation, I'm simply going to say dm naught. What does dm naught means? dm is evaluated at x bar naught. It is evaluated at the base state. It is evaluated at the base state. Everybody in the place? Good. Now if you continue like this, what is the equation you get? Delta xk plus 1 is equal to dmk delta xk. This talks about the transition from 0 to 1. This talks about the transition from k to k plus 1. From 0 to 1, the matrix is evaluated at time 0 at the base state. The transition from k to k plus 1, the matrix is evaluated at the base state at time k. This is a linear equation. So let's talk about that now. The model is nonlinear, but the perturbation to a first order approximation propagates as if it were a linear system. So, are you with me? So that's the matrix. Now, this system can be easily solved. So I'm now going to write down explicitly what that one is. So delta x1 is equal to dm0 delta x naught. Delta x2 is equal to dm1 delta x1. So let's just, I want to see the patterns in here. So delta x2 is equal to dm1, substitute this in here, dm0 delta x naught. So if I continue this in this vein, my delta xk is equal to dmk minus 1, dmk minus 2, all the way to dm1, dm0, delta x naught. So what do I have done? Look at this now. I have exactly what I want. In here, in order to be able to compute the first variation, I need the perturbation propagated at time k. So I would like to express this in terms of what is known as delta x naught. So this tells you the dynamics of propagation of perturbation. So in order to be able to, so what is this? This is a product of matrices. Why do I talk about product of matrices? I know it's an expensive thing, but we are doing analysis. We are not doing computation. Are you with me? So what are the rules in computation? Never multiply matrices unless that is what you want. Never invert matrices unless that is what you want. So I will do these operations numerically, but I'm now talking about the analysis. Yes, sir. Louder, I want everybody to hear you.
This is our tangent linear model.
This is called the tangent linear model. How many of you know that? How many of you have heard of tangent linear system? How many of you knew what it is? That's right. All of you? It's also called variational equation. So tangent linear system, what does it do? It tries to provide a framework by which you can capture the dynamics of propagation of the initial perturbation. Okay, now let me quickly do it. I'm not going to do it. Suppose I didn't perturb the initial condition, I perturbed the parameter. The solution changes, right? So can you compute the change resulting from the change in parameters and how it propagates? That's right. I want you to think about that. It's a non-trivial task, but it's a good thing for you to think about. Where is coming from? Oh, right here.
So you told that the future depends only on the present.
Yes.
Right?
Uh-huh.
So when we are calculating del of xk,
That is dynamics, but I'm still trying to solve. This is present. I'm going to compute the future. So I go from here, I go from here, I go from here, I go from here. I want to find out how much this depends on that. The dynamics captures the deterministic principle. The dynamics M tells you that if you want to be able to compute xk plus 1, it is enough to know xk. But I want to know xk in terms of x naught. Are you with me?
shouldn't we do it iteratively?
That's exactly what I have done. You are with me, except that you didn't look at the board. That's what I'm doing, right? x1, x2, I substituted it, I got the pattern. If I get the pattern, I didn't want to keep doing it, boom, I predicted it. So it is that. How the perturbation at time k is related to the perturbation at time 0. Are you with me? We are not trying to do anything against determinism. What does determinism say? If you want to know the future, if you know the present, that is enough. But what do I want? I want to know why what happened here because of what happened 10 days ago. That means I'm trying to animate it, right? Instead of saying it in words. So that's what I'm trying to do here. Okay, so this is the product of matrices. What do? I'm now going to concoct a new symbol, k minus 1 dot 0 x naught, where dm k minus 1 dot 0, essentially the product of these matrices, dm k minus 1, dm k minus 2, dm 1, dm 0. Please remember, the order is very fundamentally important. Why? Matrix product is not commutative. Okay, so in here, I started this with a function of x naught. There is x naught nowhere to be found. So in principle, the right-hand side is an implicit function of x naught. I'm trying to make that dependence explicit. In order to bring in that explicit dependence, I'm going to consider the first variation. But before I go further, can I have an explicit dependence there also? Look at this now. Let's try to iterate this guy. x1 is equal to m of x naught. x2 is equal to m of x1 is equal to m of x naught. So what is this? This is m of 2 of x naught. We all know that that's called iterated maps. Yeah.
Why do I not take care of R at each time instead of
Where is R? Which R?
R is our observation.
There is no observation here, buddy. It's all dynamics.
Only perturbation.
I'm talking about a separate problem. I'm talking about quantifying the propagation of perturbation as seen by the dynamical system to a first order occurrence. Good. Are you with me? Come on, guys. Good question. I'm glad you are all opening up. Yeah. Louder. I want everybody to hear you.
This perturbation and X.
No, this is the original this is the mother perturbation. These are all child perturbation. I am trying to relate the child perturbation to the mother perturbation.
It's somewhat we call it TIFR exponent. That's
What
what.
that?
TIFR exponent.
No, that's a different thing. Don't go there now. We call so many things, so many places. So don't go to other places. If you want to talk about labor exponent, we will talk to you coffee later. Yeah. You will see this matrix in computing the Lyapunov exponent. Your guess is right, but I'm not going to go there. I'm not going. Are you with me? Good. So let's look at this now. I wanted this. I now have this. This is made for each other. What do? I substitute that in here. I know it will take a little bit more longer for you to write it down, but I have the liberty of erasing and putting it in here, right? Let me do that. D m k minus 1 dot 0 delta x naught. Yeah, I want to tell you a couple of things now. If you want to be able to find the state at time k from time 0, you have to do the iterated maps. The notion of iterated maps in chaotic literature, especially with discrete time chaotic analysis, is one of the fundamental ways in which you analyze. Are you with me? Maybe that's what triggered your thought process, perhaps. So I have a quadratic map. I try to iterate it. I'm trying to talk about properties of iterates of quadratic maps. That's one of the fundamental tools in sensitivity analysis. Yes, sir?
Sir, how to perturb it? By what extent?
I don't know what it is. Whatever it is, I'm going to perturb it and find out what it should be. Good question. I don't know what it is, but I do know I have to perturb it. So what am I seeking? I'm seeking the optimal amount by which I need to perturb, such that from the perturbed state, the new solution will give rise to a model counterpart of observation that will match the actual observation. You all have an aha here? Hey, we are now going to play the end game. We are one step closer to the so-called adjoint dynamics. That's where the thing comes in. Ax y is equal to x A transpose y. So this looks like A transpose y. This looks like x. So I can say this is equal to, k is equal to 1 to n. I have to take the transpose. So if this is A transpose, this is A. So this is the transpose of that. I have to take the transpose of this. D m transpose k minus 1 colon 0. This is a monster of a matrix. Are you all in the place? But I can handle it. D h transpose r k h of xk minus zk. Come on. Where is this dkxk? They are all evaluated at the appropriate time. I simply don't want to carry too much of burden in the notation. You all know what that one is. This is not a constant matrix. This matrix changes. Delta x naught. Excuse me?
RK inverse.
RK inverse. Thank you. Thank you, sir. Okay, from fundamental principles, what do we know? fundamental principle tells you the first variation must be the net product of the gradient delta x naught. Here I have delta x naught is equal to this. By combining these two, what did I get? I get what I want. Is equal to dm transpose k minus m colon 0 dh transpose rk inverse h of xk minus z. Summation. I have to have summation. Sorry. Why does the summation come in? Now let's look at this now. I should be able to, I should have written one more step. This is equal to yeah, I think that's a good step for us to look at. Comma. You remember the property we have used? What is the property we have used? So I have joint property, I use the fundamental property, I use this property, I got this. So I have two expressions like this. These two are the same, so this must be the gradient. How many heard me? Good. So this is a monster of an equation. Nobody can handle it. So what do we need? We need to be able to get a clever recursive way of computing. Why this is the monster of an equation? Let's look at this now. This is the vector. This is the matrix. Matrix vector. So let's look at this now. Matrix vector is n square. Matrix is n cube. So if I go this way, it is n squared. If I go this way, it is n cube. Make it thing. So I'm now going to express a symbol. Let f of k be equal to dh transpose k rk inverse h of xk minus zk. So this term that comes in here, I'm going to call it f of k. So this essentially tells you delta j of x naught is equal to summation dm k minus 1 colon f of k. Now what is the k? This involves matrix product, but I can rewrite this in a way that does not, and that gives rise to the following. Now define lambda n to be fn. Hey, we know what fk is, right? How many of you heard me? Come on, guys. I concocted a new symbol to represent this because I don't want to write too many things. I have observed, the last time I have observation is capital N. At capital N, I know this quantity. So I'm now defining a new quantity called lambda n. Lambda n is a vector. Now let us see what is the size of that vector very quickly in here. This lies in Rm. This is Rm by n. This dh is equal to, dh is m by n. So dh transpose is n by m. So n by m, m by m, m by m. So this belongs to Rn. So this belongs to Rn. How many heard me? That's right. So I'm trying to define a new entity called lambda n. This lambda n is very similar to the Lagrangian multiplier that you will get. I will talk about it in a minute. And now define a new set of lambdas recursively given by the following equation. Lambda k is equal to dm k transpose lambda k plus 1 plus f of k. This is for, so lambda n, this is for k is equal to m minus 1, m minus 2, all the way up to 1. Okay, in my book I have assumed the observations are available even from the initial time. So if you did that, it will become from 0 to here. If you come 0 to here, it will become 0 to here, and that shouldn't change too many things. I'm assuming I'm having the facility of one more observation that will make things a little bit more clearer. Nothing changes except that I'm assuming I have k plus n plus an observation from 0 to n. Are you with me? Come on, guys. So 0. So can we now do that, please? And this is going backward in time. Compute lambda naught. It can be shown lambda naught is delta jx naught. Amit, how much time I have? A few minutes to wind up? About 5 minutes to wind up? When do I stop? 5 minutes to stop. Okay, good. Okay, so,
When you get a good stopping,
excuse me?
when you get a good stopping point.
Yeah. Okay, we can probably revisit some of the nicer issues maybe this afternoon. Okay, good. Are you with me? How many of you are with me up to this? Good. How many of you are with me with respect to the cost? Matrix, 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 vector. That's good. So I need to avoid matrix, matrix computation. So what is the trick? If you rewrite, if you introduce this set of recurrence relation or iterative things that goes backward. So now I'm going to describe this. This is time 0. I went ahead. This is time n. So the model is on forward. Now here I'm starting with lambda n, and I'm computing one at a time, lambda n minus 1. Lambda n minus 1, lambda k, lambda naught. So the backward. So using the forward run and the backward run, once I get lambda naught is equal to delta jx naught, the gradient. Secondly, I also want you to remember Fn, lambda n is a vector, this is a matrix, matrix vector plus vector. This operation is only on square. How many of you may? Now what is the homework? This is a simple linear occurrence, right? You should be able to substitute back, substitute back, substitute back, substitute back. If you did substitute back and collect all of them, your lambda naught expression must be equal to that. Homework problem.
Why don't you get delta inverse?
What's that?
Why don't you get delta and inverse?
Inverse in here? The transpose, I'm sorry. Sorry, my bad handwriting. Okay.
It's important to the intuition. When you talk about going backwards, it seems like dm inverse or
That's right. That is the magic of the adjoint. So this is why this called the adjoint system. And do you remember transpose of a matrix is called adjoint and finite vector space? So that's called the forward. This is called the backward. This is the adjoint, and hence the name first order adjoint. How many of you with me? Okay, good. So, okay. The lambda naught is the last thing you need to compute. Lambda naught is the thing that you compute last. Because to compute lambda naught, I need to compute several things. But okay, I don't want to dampen your movement. Go ahead, but first or last, it has to be computed. Never mind. Go ahead.
Because for delta k, we need
Not delta, delta xk. There's no delta k.
lambda k.
Lambda k, good.
We need to know that dm transpose of k.
That's right. So what is it I'm trying to do? Dm transpose of k, what is this? This is the model Jacobian evaluated at time k, but I have already run the model forward. So run the model forward, collect the state. Using the state information, I can compute the Jacobian at each of the state, each of the times at which the state is known. So that gives you this quantity. I take the transpose of that, that's the adjoint. Then I concoct a new recurrence. So what is f of k? So let us just say f of k very quickly now. This is the error of the innovation. The difference between the model forecast and the actual observation is the innovation. What is RK inverse this? This is the normalized error. All of it in place? This error lies in the observation space. So let's quickly look at this now. This is Rm, this is Rm. Sorry. So RK inverse h of xk minus zk lives in this space. What pulls it from here to here is this operator, dhk. So dh transpose k pulls it in here. So what is f of k? F of k is the normalized innovation as viewed from the model space. All of you? This is the normalized innovation as viewed from the model space. So that helps to bring it here. Once it brings it here, I'm doing calculation in the model space. So lambda n is n. N is the dimension of the model space. All of it? So once the gradient is known, what do we need to do? Now we need to do the good old thing. I have x naught. I have gradient of x naught. Gradient of x naught. I multiply that by some beta. I don't want you to confuse that with that. I want to minimize. I'm going to compute this. This becomes my new x naught. How many of you may? This is the old x naught. This is the gradient of that. Using a simple gradient method, you get a new x naught. Repeat the procedure. Until what time? Until you don't see much improvement in any one of the related quantities. So what is the adjoint method? Adjoint method enables, so what is summary? First order adjoint method is the methodology by which you compute the gradient of the objective function which measures the weighted sum of squared errors. Once you compute the gradient, you are not done. You have to use it in optimization procedure to be able to go towards the minimum. Okay? So it's a two-part thing. Run the model forward, run the adjoint backward, get the gradient, update the initial condition. So I started with the old one, I get to the new one. Run the model, keep looping, and that's 41 mathematically. Okay, we are done with in about slightly 5 minutes over time. If there are questions, I'm sure you may have, and we have a question and answer session this evening. A couple of guys told me that they wanted to see the details of SVD, right? I hope you didn't forget. Good. I hope you remember to ask. Likewise, if you have any other questions on these and other related issues, we will talk about that. Any other questions? If not, we will break for coffee and come back. Thank you.